Today, I'd like to talk about our development of directly liquid-cooled integrated substrate for power module. Let me introduce myself. I am Hideo Osanai from Dowa Power Device located in Japan. I am in charge of R&D as Managing Director. I am a research expert for bonding technologies and metal ceramic substrates. Our company is one of the world's top-class metal ceramic substrate manufacturers. Outline of my presentation is firstly motivation. Secondly and thirdly, I talk about materials, bonding method, and structure study for integration of power module. After that, I explain the heat dissipation performance and reliability evaluation of that. Finally, I summarize and talk about the future of our technology. The figure 1 shows the cross-sectional structure of a conventional power module and new structure after integration. As you know, a conventional power module is complicated and consists of many parts, and it requires multiple assembly steps. Our goal is to reduce components, assembly steps, and bonding interfaces by integration of metal ceramic substrate, base plate, and cooler. When aiming for an integrated structure, we first examine the insulating materials and conductive materials. Insulating materials are typically resin, rubber, or ceramics, but ceramics are preferred in terms of thermal conductivity. Therefore, we selected aluminum nitride as best ceramics. Next, among metallization materials, we selected 99.9% aluminum because of its material cost and bonding properties. Table 3 shows comparison of method between metal and ceramics. The division method and the AMB method are very famous, and this sheet shows those features. By comparative tests, aluminum directly bonding method was selected as the best bonding method regarding the bonding temperature and bonding strength. Benefit of this bonding method is that the various 3D product shapes can be easily produced by the design of mold. Another benefit is that the bonding strength is extremely high. At figure 2, you can see each atom arrangement up to the boundary of the aluminum directly bonding method, and direct bonding is achieved. Also, there were no microscopical bonding defects. From here, I introduce how we examine the structure for integration. You see the first model of an integrated substrate. The size of base plate part is 140 mm by 90 mm. Ceramics is 0.635 mm thickness, and the circuit layer is 0.6 mm thickness. We simulated the thermal behavior of the first model at 270 degrees Celsius by FEM. Figure 4 shows the contour of the quarter model. The axis shows the deformation at 270 degrees Celsius. We found a deformation of about 5 mm, which is quite large. Figure 5 shows the stress generated in aluminum nitride at this time. It indicates that a principal stress of approximately 310 megapascal occurs, which is relatively small. However, because of large curvature deformation, it is difficult to assemble. Next, let me introduce how we improve the model. We added an additional ceramics layer into the base plate part. By this update, the model's vertical direction arrangement is symmetrical among aluminum and ceramics. Figure 7 shows a counter figure of the z-axis deformation of two ceramics model at 270 degrees Celsius. The warpage has been dramatically reduced. Figure 8 shows the stress in the ceramics layer, which reduced to 160 megapascal, 50% reduction against the first model. Since the results of two ceramics models were excellent, we decided to proceed to the next step. This sheet shows an experimental sample of two ceramics models. When heated up to 300 degrees Celsius, no warpage occurred. This result confirmed the calculation results. Next, we evaluated the heat dissipation of two ceramics models against the conventional module structure by simulation. Table 4 shows components of conventional model structure with aluminum nitride substrate. Table 5 shows the module assembly with two ceramics model integrated substrate. This sheet shows the applied CFD calculation method and conditions for determining temperature difference between chip and cooling water and thermal resistance. Figure 10 and 11 show temperature profile when the conventional structure and the integrated substrate generates 3 kW of heat. When using integrated substrate, delta T and thermal resistance of chip to cooling water were about 25% decreased. This result was realized by eliminating the system soldering and TIM. This sheet shows the results of reliability evaluation. We tested samples under minus 40 degrees Celsius and 150 degrees Celsius for 3,000 thermal cycles. We didn't find any cracks in ceramics or peel-off effect. It was a very good result. Let me summarize the results. We have succeeded in integrating a metal ceramic substrate, base plate, and cooler. High reliability was achieved by using two ceramic structure, which enables significant reduced warpage and minimized principal stress. By eliminating system soldering and TIM, we gained improved heat dissipation by approximately 25% compared to the conventional modules using ALN AMB. This enables downsizing the modules. Also, by using light aluminum, the weight was reduced by approximately 70%. Most important, module costs can be reduced by module downsizing and reduced the assembly costs. In addition, lower cost aluminum oxide ceramics can be used instead of aluminum nitride ceramics. Future, we believe that this technology will have huge contribution for next generation power modules, which are used for high temperature application and high voltage application. In concrete, we are planning further variants of this technology. A multi-insulation type for high voltage by the less concentration of electrical field. Low inductance technology with wire hole for big motor drive. A single ceramics type for double-side cooling for base plate less module. And an aluminum alloy type for high temperature application. Thank you very much for your attention. If you have any questions, see you at roundtable session.
Ladies and gentlemen, welcome to this presentation from the company Fuji Electric about our 4th generation aluminium direct water cooling structure with high reliability for automotive electrical systems. My name is Steffen Ewald. I'm an application engineer working for Fuji Electric Europe, and I'm responsible for our automotive products. Coming to the contents of this presentation, first we will talk about the background of the development, then we will highlight the key technologies of our 4th generation direct water-cooled power modules, then we will come to the features of our 6-in-1 module, and finally to the conclusion. On this slide we can see the trend in the output power density of our power modules. The basic trend in the industry is to increase the power density so the modules can become more compact or the power can be increased. On this slide here you can see our industrial modules on the blue line, then our 1st generation modules which used copper pin-fin cooler. These are automotive products here with the orange line, and finally in 2012 we presented our first directly water-cooled module with an aluminium cooler. And since then we were able to increase the power density by a huge amount. This module here, our 3rd generation, was released in 2017, the M653, and just now in 2020 we have released the M660, and we were again able to increase the power density by 1.6 times. We achieved this by both improving the cooling technology but also with more efficient chips. On this slide you can see an overview of our products. So in the range from 50 to 100 kilowatt, we're seeing our M655 module, which is supposed to be released next year. Then already on the market in 2017 is our 800 amp module. Currently released is the M660, which comes in 2 options with 800 and 1200 amp, catering from around 150 to 200 kilowatts. And we are still wanting to increase the power density even further based on silicon technology as well, with a new product which is even more compact than the M660 and thus giving you an even higher power density. But it is too early to talk about a release yet. Now we come to the key technologies of our 4th generation direct water-cooled power modules. The 4 pillars which we are focused on are lightweight, compactness, high reliability and high power density. Lightweight we achieve by switching from copper to aluminium water cooler and also reducing the overall module size. The compactness in general is achieved by our very low thermal resistance water cooling technology and also by a new generation of RC IGBT chips which have less losses compared to previous generations. High reliability we achieve by having a low warpage amount, good solder connection, and also we have on-chip sensors on our RC IGBTs. We have current and thermal sensors, so we have a very fast reaction to overload situations. And finally, the high power density is achieved by our continuous operating temperature of 175 degrees centigrade and also a high current density. Now we are focusing on the water jacket. This slide is showing the 4th generation structure concept. The left graph is showing the trade-off relationship between the thermal resistance shown on the y-axis and the pressure loss shown on the x-axis. Usually you want to achieve a very low thermal resistance. However, if you do so, you usually will increase the pressure loss. You could counter this by making the cooler thicker, then you can decrease the thermal resistance without increasing the pressure loss, but your power density will decrease. So there's always a certain trade-off. And coming to the right side, here we can see the thermal resistance ratio of each layer within the module. The top is showing the chip in light blue, then in orange we have the solder between chip and substrate. Gray, yellow and blue are showing the ceramic substrate itself, with the top copper layer, the ceramic material and the bottom copper layer. Then in green we have the solder between the ceramic substrate and the aluminium fin base. And here in blue we show the aluminium fin base itself. This is what we are focusing on right now, because at Fuji we were able to reduce the thickness of this aluminium fin base to 1/5 compared to our 1st generation. This aluminium fin base is the thickness of the base plate in a conventional module. And by decreasing this thickness, we were able to reduce the thermal resistance by a huge margin. Here we can see a thermal fluid analysis of our 4th generation cooler structure. On the left side you can see a schematic of our cooler with the bottom base plate, then in blue arrows showing the water inlet and water outlet. Then we have the fin structure shown in this copper color block here. On top there is the fin base, which is semi-transparent here in this graph. On top of this fin base we have the ceramic substrate and the chips. The thermal resistance is of course measured from the junction temperature of the chips to the water inlet temperature. On the right side we can see the thermal resistance over the flow rate with different fin base thicknesses. At a relatively low flow rate of only 0.5 liters per minute, you can see that all these points are close together. But if the flow rate increases, then the benefit of this thin fin base thickness is increasing. So at 3 times the flow rate, we have reduced the thermal resistance by quite a bit. And also you can see the effect that the thick fin base shown here on top and the thin fin base shown here at the bottom is becoming much and much bigger. So when we increase the flow rate, the effectiveness of the thin fin base is strongly increased. Now we can see a simplified cross-section of our first generation water-cooled modules and our fourth generation water-cooled modules. The fin base thickness shown in here has been reduced a lot compared from the first to the fourth generation. In the first generation we had this conventional fin base thickness and the vertically aligned fins. They go down here into the water jacket. Then you have an O-ring around all of the water jacket, and then the top of the module is screwed down into the water jacket, squeezing these O-rings tight to get a waterproof connection. In our fourth generation, you can see there is no gap between the top and the bottom. So the fin base and the water jacket are one part, and also the internal structure has no gap as shown in here. So the water cannot bypass below, and every bit of water running through the cooler is directly used to transfer the heat away. Also, you don't have any leakage issues because it's all one solid connection. We were able to reduce the thermal resistance by 43% compared to the first generation and increased the power density by a factor of 3. Now we come to the reliability section. On this slide we can see the reliability improvement. In our first generation, as shown before, we used an open pin fin type structure, and therefore we needed a relatively thick fin base, thus increasing the thermal resistance. Now on the right side, in our fourth generation, we can have a very thin fin base without having a warpage issue. And this is because the top, the bottom and the fins are merged together to be like one part, so it's a very rigid construction. And this means even looking at the graph at the bottom, even with this thin fin base density, we have very little warpage amount. Then on the right side, we come to the thermal cycling capability. The red graph is showing the first generation and the blue graph is showing the fourth generation. And as you can see, with a thicker fin base, if you move to the right on this graph, you will decrease the number of cycles that your module can withstand. However, with this open cooler structure, you need the fin base thickness in order to have a reliable module. With our fourth generation cooler, we can have a much thinner fin base while keeping a high number of cycles. And here we can see the thermal cycling capability in a little more detail. So this graph here is showing the number of cycles that the first generation could withstand, and on the right side we can see the number of cycles that the fourth generation could withstand. We were able to increase this by 1.4 times, even though the tensile strength of our solder material, shown in these gray blocks here, has become lower compared to the first generation. On the right side we can see a typical destruction image of a thermal cycle. So if you have a lot of thermal cycles, the solder crack will start here at the outside of the connection and then move inwards, thus increasing the thermal resistance even more. Now we come to the features of our 6-in-1 module. Here you can see the dimension of the module. So it's 178 millimeters wide and 160 millimeters deep. The bottom side shows you the closed cooler structure with only one inlet and one outlet. So you only need 2 sealing rings here and here to have a waterproof connection. The module is rated at 750 volts. It is available actually with 800 amp and 1200 amp. and we have a 175 degrees continuous operating temperature, and as mentioned before, we are targeting around 150 to 200 kilowatt. The module has a very high power density, it is lightweight, compact, and very thin. Now we come to our conclusion. The main focus on our 4th generation water cooler was to increase the cooling technology itself by reducing the fin-based thickness and optimizing the fin height and shape to have the perfect trade-off between thermal resistance and pressure drop. We were able to decrease the thermal resistance by 43% and at the same time increase the power density by a factor of 3 compared to the 1st generation of water coolers. The reliability improvement is also significant with 1.4 times higher thermal cycling capability, despite using a solder material with a lower tensile strength. We thank you very much for this presentation, and please keep in mind that there will be a discussion round afterwards where you can place your questions. Thank you very much for your attention, and goodbye.
Hello, Peace in Europe Digital Days. This is Tim Pollum from Silicon Austria Labs presenting the paper Spatial Thermal Frequency Response Measurement of Power Semiconductor Equipment. Co-author on this paper is the late Professor Bob Lorenz of the Wisconsin Electric Machines and Power Electronics Consortium at the University of Wisconsin-Madison. I'm also a recent alum from WEMPEC at UW-Madison, and I have a mechanical controls background, which started off with a BS in mechanical engineering from Michigan State University. Currently, I'm a scientist in the Division of Power Electronics at SAL Silicon Austria Labs, and I have broad research interests in power conversion, which includes power electronic converters and heat transfer, along with the other topics I've listed here below. Here's an outline for this presentation. The presentation begins with background and motivation and then investigates analytical modeling of transient heat transfer before getting to the heart of the presentation, and this is building a test setup to do system identification experiments, which includes results, and finally we'll have a conclusion section. Everyone wants compact, responsive, and long-lasting power electronics. This paper is dealing with the topic of how losses in semiconductor devices initiate some sort of transient thermal response, which ultimately is leading to harmful thermomechanical stresses and state of health degradation. If we consider a design problem of power electronics where we have components and we need to decide how close can they be, this paper in the background is trying to help us better solve a common design problem of what are the implications of this specification and what are the key criteria for its optimization. In the back of our minds, we might have some sort of idea that the power density of a converter and the expected lifetime of a converter have some sort of trade-off relationship with each other. So this paper is aiming to develop a powerful methodology for navigating these multivariable design problems we have in power electronics. This paper included an analytical analysis of transient conduction heat transfer for the problem shown here. And this is based off of the illustration I showed in the prior content slide, where we had the design problem of how close can we put the power electronic components together. This is illustrating an abstracted version of this problem in which we have one device's loss is represented as a boundary heat flux, and we're trying to solve for the temperature distribution as a function of the spatial variable x and also as a function of time. Ultimately, we derive in the paper a normalized spatial thermal frequency response, which shows that the normalized temperature rise at the boundary where the losses are is significantly higher than on the tip of the domain, which matches our intuition. Ultimately, we derive a scaling solution which describes how the frequency response function magnitude is a function of the harmonic loss dissipation on the boundary and also as a function of the spatial domain variable. So a relation linking dimensions to the temperature rise, which is a very influential factor of power density and reliability, was formed, and this allows moving forward for creative exploration of design space, and it motivates what this paper considers additionally. So the next section is about measuring these types of spatial temporal heat heat transfer frequency response functions. Fundamentally, this paper presents a method which is based on recently established literature. So we're harmonically modulating devices in a semiconductor device and monitoring the thermal response. And a signal flow diagram is shown here in which we have the converter, which is digitally controlled, and ultimately current and voltage measurements on board in the converter, this was a half-bridge type of converter, are used to estimate the losses and the temperature response via a temperature-sensitive electrical parameter. The host PC, which is running all the auxiliary equipment, also is interfaced with an infrared thermal camera. So what this paper is adding is the time-synchronized measurement with infrared thermography along with the onboard measurements of a T7 losses. Ultimately, the goal is to form these discrete frequency electrothermal impedances. An image of the test setup is shown here. What I want to focus on the most is that we have a converter PC, so the half bridge was actually oriented in this vertical way in which the base plate of the mock-up power module was oriented normal to the infrared thermal camera. The mock-up power module is displayed here. It was implemented in a half bridge, operated in a conduction loss modulation mode, as I mentioned, and it's a single active Fuji silicon MOSFET bonded to a base plate with a screw-in thermal interface material. The thermistor was not used in this study, but rather in other studies. Compared to a commercial model, these initial tests of thermal frequency response measurements used a hardware prototype having just a few features that we could control in the lab. I mentioned that we used optical temperature sensing in order to monitor the thermal response as losses were dissipated harmonically in the MOSFET chip. And to be specific, we monitored the response along one of the two available vectors. So we looked in the transverse direction as the power MOSFET was dissipating conduction losses. Going now to measurement results. Recall that in the first content section of this presentation, we presented the scaling law, which linked the frequency response function describing heat transfer to the harmonics of the loss dissipation and also the spatial location. So what we were able to extract after measurement and processing was magnitude and phase response, frequency response data. So we have the magnitude and phase response components of the complex FRF data represented here as a function of the driving frequency, and this is the driving frequency of the conduction losses in the MOSFET component, and also the pixel. So this is pixel 0 to 60 extending from the left-hand side of the MOSFET to the right-hand side of the base plate. Now imagine that we're looking into one of these 3D plots in the direction of this here. So this page is now using color in order to show how the certain spatial domain features, such as the MOSFET, the transition between the TO247 package and the base plate, and also the base plate surface, correspond to the data that we extracted. The top plot is showing data with a logarithmic y-axis and a linear x-axis. The bottom plot is showing the data on a linear plot, and we can see that we have additional detail of the semiconductor device surface that we're able to see with this linear plot. Ultimately, correlation between spatial domain features which we knew before doing the experiments and the resulting data is visible. A final thing that I want to mention is the dashed line in this top plot. This was after manipulation of the thermal interface between the MOSFET and the base plate. This was covered in another paper, but what I want to highlight and emphasize is that these plots, really we should be periodically extracting them during accelerated lifetime tests for comprehensive characterization of what thermal mechanical stress is doing to our assemblies. To conclude, with a setup involving a digitally controlled converter and infrared thermography, we were able to make measurements of spatially varying frequency response functions. And these are telling us in a detailed way how geometric dimensions dictate the relationship between the loss dissipation in our devices and spatial temperature gradients. Keyword here is reliability. We were able to see features or magnitude responses that varied on the order of at least one order of magnitude, depending if we were on the semiconductor chip or on the base plate substrate. And this tells us that we can see spatial domain features in these measurement results, and an interesting thing potentially. Not in this presentation. Yes, we need our measurement equipment to be synchronized, and the errors in the phase delay metric are proportional to the fundamental period of the loss excitation. And at the beginning of the presentation, we used heat transfer modeling to synthesize a scaling law that can be used to specify geometric dimensions relating a component's transient temperature rise and loss dissipation. Bottom line in this paper is that we expect future technical leaps, which is potentially more formally investigating feature extraction, will help us to make this measurement methodology serve reliability and power density ambitions. Thank you for your attention in this presentation, and please, if you're able, attend the thermal management Q&A session on Tuesday, July 7th.
Good morning, everybody. It's my pleasure to give a talk about our ultra-fast switching 3.3 kV silicon carbide high-power module. The presented silicon carbide LINPACK has almost order of magnitude lower switching losses compared to the state-of-the-art silicon version of the module. The work was done by Slavo Kitchen, Ralf Burkhardt, Jean-Yves Loisy, Francisco Canales, Muhammad Navas, Gernot Stampf, Pauline Morin, and Tobias Keller. All was working at ABB Power Grids and ABB. Let me start with a few words about myself. I received electrical engineer and PhD degrees from Slovak Technical University in 1996 and 2001, respectively. In 2001, I joined the Department of Physics at ETH Zurich in Switzerland as a research assistant. Currently, I'm principal scientist with the Group of Packaging and Advanced Materials at ABB Power Grids Research in Switzerland. As you can see, the outline of the talk is very simple, and therefore I directly proceed to introduction. Fast switching capability is one of the most attractive properties of silicon carbide power devices. However, in order to fully benefit from this fast switching capability in high power applications, the power module must fulfill certain requirements. And it is not always possible to directly replace silicon by silicon carbide devices and achieve targeted properties of the module. Here are the main challenges. First, inductance of a power module must be low enough to minimize turn-off overvoltage and oscillations. Second challenge is a small area of silicon carbide devices. Therefore, it is necessary to parallel many devices to achieve competitive current rating. It means that it is necessary to provide electrical connections for all these devices and still achieve balanced current sharing and switching without critical oscillations. And finally, today a typical silicon carbide module is built on a platform of a fully optimized silicon module, and developers are trying to achieve reasonable performance of such silicon carbide module. In order to address all aforementioned challenges, we propose a multi-level or stacked substrate module concept. The concept shows following main benefits. First, it allows to parallel many silicon carbide devices and still achieve low inductive design and balanced current sharing. Second, conventional packaging technologies are used to assemble the module. Third, benefit is a good thermal management of the module. The multi-level concept was several times successfully applied to build high-performance silicon carbide modules on the platform of ABB module LINPACK. 3.3 kV silicon carbide module version presented today shows another improvement of switching performance. More details about the multi-level concept one can find, for example, in our ISPD paper from 2016. 3.3 kV silicon carbide LINPACK is a half-bridge module which can be rated 450 or 900 amps. The rating depends on number of MOSFETs placed on the substrate. Today we present module having current rating of 450 amps, since this version allows direct comparison with the silicon LINPACK. It means that in the module were parallel 20 MOSFET per side. The module has tri-inductance of 10 nanohenry. In order to maximize the current rating, the module does not include the usual Schottky diode. Therefore, the MOSFET's body diode has to be exploited during switching commutation. On the next slides, we discuss results of static and dynamic measurements carried out to investigate performance of the module. Slide 9 shows typical output characteristics of MOSFET and forward characteristics of MOSFET's body diode. Measurements were done at room temperature and junction temperature of 125 degrees C for both high side and low side of the module. Measured RDS on corresponds to RDS on of 20 MOSFETs connected in parallel. The value is only slightly higher due to the contribution of module parts. It is interesting to see that despite of negative voltage of minus 5 volts applied during measurement of body forward characteristics, MOSFET's channel contribution seems to be still present. And finally, we observe only small deviation between modules for both output and diode characteristics. This is an important prerequisite for a satisfactory performance of modules connected in parallel. Modules transfer characteristics and threshold voltage are shown on the slide 10. Measurements were done at room temperature and at temperature of 25 degrees C. The transfer characteristics were measured on 3 different modules. It means that the picture on the left shows currents measured on 6 different switches. One can see that the current flowing through any of the switches at any applied gate voltage differs from the current flowing through the other tested switches only by a few %. As expected, the threshold voltage was much lower at 25 degrees C compared to room temperature. Again, the difference between both compared switches was not significant. It means that our results indicate that paralleling of tested 3.3 kV silicon carbide limp packs should be possible with minimal derating. A double pulse test was used to investigate switching performance of the module at different operating conditions. Inductance of the test setup was about 35 nanohenry, including inductance of the module. A gate driver developed for silicon carbide module was used in the test. Slide 11 illustrates an impact of gate resistor and temperature on switching transients. Observed ringing is reasonable for applied test conditions. The figures also include switching transients of the body diode, which, to the author's knowledge, are the first published for a 3.3 kV silicon carbide high-power module. The diode's transients showed both expected effects, a higher reverse recovery peak as a result of higher junction temperature and as a result of a lower gate resistor. However, an impact of turnout losses was not so significant as reported in literature. According to our opinion, results indicate that the use of the body diode would be suitable for high-power modules. More detailed analysis of switching performance of the module one can find in the paper. Switching transients were used to determine switching losses of the module. Picture on the left-hand side illustrates an impact of junction temperature on these losses. It seems that the influence of the temperature was not significant. The losses were measured using DC link voltage of 1.8 kV and gate resistor of 1.5 ohm. Picture on the right-hand side compares the total switching losses measured for the 3.3 kV silicon carbide limp pack with those of silicon module version under same conditions at current of 450 amps. As shown, the total switching losses of the silicon module were about 1410 mJ at room temperature and 2010 mJ at temperature of 125 degrees C. The total switching losses of the silicon carbide module were considerably lower. At room temperature, total losses of 200 mJ were measured, which is 7 times lower compared to the silicon module. The difference was even larger at temperature of 125 degrees C. There, the total losses of silicon carbide module were about 205 mJ. This means that switching losses of the silicon carbide module were about 10 times lower compared to the silicon module. Such low switching losses of silicon carbide compared to the silicon have so far been typically measured only for discrete devices and not for a high-power module. In order to gain a more comprehensive understanding of the practical opportunities of the presented silicon carbide limp pack, a comparative study at the converter level was carried out. For this purpose, the achievable performance of the silicon carbide module version was benchmarked against the silicon counterpart considering the two-level medium voltage inverter showed on the slide. The details of the benchmark are again presented in the paper. Here, we provide only short summary in the form of a table which shows achievable performance for the different design strategies. In our study, 3 parameters of the converter design were addressed: operating junction temperature in design 1, achievable nominal power in design 2, and switching frequency in design 3. Red circles highlight improvements achievable by replacement of silicon module by silicon carbide limpec. Let me summarize the talk now. 3.3 kV 450 amp silicon carbide half-bridge module built on the IBB's high power module platform limpec was assembled and tested, extracting its main static and dynamic characteristics. A low inductive module based on multi-level module concept is exploiting MOSFET's body diode. Only small deviations between modules were observed for a measured output, transfer, and body diode's forward characteristics and threshold voltage. These are important prerequisites for operation of modules connected in parallel. Our results indicate that the use of body diode would be suitable for such high power modules. Total switching losses were up to 90% lower compared to silicon module version. Superior loss characteristics offer attractive design opportunities at the converter level. This is everything from my side. I'm looking forward to a discussion during the question and answer session. Thank you for your attention.